Hello, this is the INB382 shadow mapping demo. So we're just going to go through the shadow mapping demo because it's a bit more complex than most of the other demos. It has a number of components, and for you to use it effectively requires a movie to illustrate this. So first of all, here we have, just in the Unity editor, because I've actually got it executing, the shadow mapping demo. So you can see it's just a couple of objects and a plane, and we look up above and here's the light source. The light source is actually a camera, funnily enough. So just to be aware, you can use these cameras as your light sources for the shadow mapping. You should be able to easily integrate that with the light spotlights you've done in the first assignment. If you have a look as well, you'll see that there is a back screen that I've put in. This is actually showing the depth map that has been generated to generate these shadows. And furthermore, I'll just illustrate that as we move the objects in and out, I might get in closer, you'll see the shadow changes in real time in the background, because you're probably used to this in most games you've played. But nicely enough, in Unity, we're able to use the editor to illustrate this, and I'll be able to play with some of the parameters to show you some of the outputs and so forth, the stages that occur in the shadow mapping. So first of all, this is a multi-pass technique. This requires that we use a render to texture approach. So if we look over here, we'll see on the left-hand side here, as I click it, that there's a depth map. Now if we look over here on the right, you'll see that it looks a bit psychedelic. I will get to that in a minute. So to create these render to textures, it's quite straightforward. You just, within your asset view, go create, and you will see render texture. I'll just create one. I won't use it for the rest of this, but you will need to do this for every light in your scene in order to create textures for the shadow mapping. So all the lights, sun and two spotlights in your scene, will require you to create multiple render textures, because, as per the theory, each depth map represents the view of the scene from the light's point of view. All right, I'll delete that because I don't like leaving things untidy. And okay, so here's our depth map. We can see it's a bit psychedelic. I'll get to that in a minute. And we'll note that that is then a parameter to any of the other rendering systems that we use, or shaders. So if we go up to the camera, so I've just called it camera, maybe I should call it light, this will do. We know that this camera is the light source from above. And if we go to the right here, we'll see that there's a target texture option, and that the inspector allows you to choose render textures. So we're using depth map because that's the only one in the scene. So what is happening here is that we are, for the first pass of our shadow mapping algorithm, we're using this camera up here to generate a render texture, and that render texture is created as part of the inspector setup. You can do it in scripts, but I'm happy for you in the assignment to use this method because you'll probably send yourself insane trying to debug it. This is actually much easier and I think appropriate for this level of the unit. Now, so we have the camera. The camera represents the light source at that position above the scene. So we can see the shadows are projecting down. And so that camera is generating the depth map. So how is that being done? Well, interestingly enough, this camera has a special script. It's called turn on depth buffer script. And so I'll switch over to that. So just recapping on what we're doing now before I get into the code. We've got the camera at the light source. We have a depth map render texture. So the camera is now rendering to that texture. As we see here, the target texture is that. But there's also a script. The script on the camera handles some of the shader magic that is needed to generate the depth buffer. You won't need to change that for the assignment, because as long as you set up a camera in the same way as done in this scene, then you'll have an adequate light mapping camera, and that's appropriate for the unit. That's why I've done it for you. So opening up that script, It's not a big script, but there's just a couple of important things that we have to put in there in order to tell the system to get itself ready to generate things appropriately. So the camera has, as we can see there, we can access itself by using the camera variable, and we are turning on that this is a depth texture camera. It's going to generate depth, not a color. So what's being spat out of here is actually a depth buffer. There's also, all right, I just set up some clear flags. I don't think that's really that important. I make the background color white. The reason why I make the background color white is because I want the furthest Z value to be the background, and so it's going to generate a white. The rendering path, so one of the things we note is that we want to use a forward renderer. Just trust me on this one, because I think the deferred rendering pipeline does not like having its shaders replaced. So this is just a trick. You don't have to check it, but just that's why that line is there. Here's another important part. We need to get this camera to generate depth, but we then need to get that depth into our other shaders. Now, Unity, in its own version of the shaders, does this internally, and it'll use lots of complex OpenGL or Direct 3D to do this. But what we can do is fudge it. And the way we do this is to replace the shaders for this camera to generate depth. Now this is something important because this will be useful for other effects we may learn in this unit. So for this camera, it's going to use the depth generation shader. So we're saying to the camera, replace your shaders with this depth gen shader, and replace all of the ones that are tagged with render type. So be careful here. I actually did this script with nothing in that space between the apostrophes and ended up in a bit of trouble because it would never replace the script with, the shader with this depth map generation script shader. So just be aware of this if you ever use this command in future cameras inside your games. Going back to Unity, so we'll see here that, all right, so the camera has got the script. That script is replacing everything in the scene. So you can see that from the camera's point of view down here, it's not red, it's actually a depth value coming in that's encoded. That's why it's psychedelic. This means that we now have a look at the shader that's used to generate that. And that's called the depth map generator. So it's a material, it has a material associated with it, of course. And that also means, just as an aside, you have to attach a mesh renderer to the camera. So be sure to look at these details when you're setting up your cameras for your other lights. You've got to replicate all of this. So the depth map generation shader, I'll just open that up here. Now this is one that I ripped off from the web. I probably should cite where I got it. That's naughty of me. But anyway, and this is a very simple shader. It's basically a straight pass-through shader for most of the components. It projects the position appropriately, blah, 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 blah. But what actually happens inside of Unity, and this is just useful for you to know, is that if you set a camera to have a depth mode, an automatic texture gets passed through, giving you a depth texture that you can play with in the shader. Note this is very useful for things such as cell shading for detecting edges. But for here, we just want to use the raw depth. We just want to pass it through. So we transform all our vertices, and they're passed out, blah. And then we come into the fragment shader. Now the fragment shader has a number of components that you're probably not aware of in this space. There's two things I should show you. First of all, this little line of code here, again, you don't have to change this for the assignment, but it's something to be aware of. It takes the depth value from the camera depth texture from the projected position, and it linearizes the Z value so that the depth value coming out is not a non-linear, log linear model. There are reasons for this. Z buffers are not recorded as a linear value of Z. They actually compress the detail in the space closer to the camera. so that you can resolve distances close to the camera and resolve very fine detail. In the distance, it doesn't matter. So therefore, what we have to actually do is linearize that Z depth so we can do some appropriate shadow mapping within the volume of the camera. Anyway, that's the depth value. Now, problem with textures is, and the problem with Unity textures at this level is we cannot store a depth texture. They only have RGBA textures. Now, if we were doing this in Direct 3D, we can specify textures that are just 32 bits of depth, and that's great. Can't do it here. So Unity, God bless them, have created a little macro which resides in this include file here that actually takes a float and encodes it into an RGBA 4:1 float. That's why the view from the camera, if I go back here, looks psychedelic. The reason for that is this is actually an encoded float split up into RGBA values. Now, if you want to check that out further, there's code on the web to sort this out. It's a fairly standard sort of algorithm, especially in restricted sort of profiles that you see on mobile devices and so forth. Something to keep in mind. Anyway, this is all done for you, but just so you know, this is the depth map generation shader, which is run within, remember, the script for the camera for the light source. So this means that the first stage is all done in theory, as you see in the lecture notes, that it generates your depth map. It's encoded, and that means we've got it ready for the next stage, which is the shadow mapping shader to actually generate the shadows. So that's the first stage done. We now move on to the second stage, once I organize my notes here. Okay, so the other point I want to make out here is I've just put this Jim Dandy little billboard, I guess. That's not a billboard, really. Right. So it's just a flat quad. Actually, that's a cube that I squished. And I've mounted the texture for the depth map onto it, just so that you've got a bit of reference for what is going on in the depth map. This is useful for understanding the theory, because as you can see, I'm moving the pill, and the pill is moving up and down inside the depth map. And then I move the cylinder, as you can see there, and you notice that the closer things get to the camera, the darker they get. The closer they get to the back clipping plane, the lighter they get. It's just the Z value. So what you're seeing in that shadow map over here is the Z value for the objects, for every pixel from the light's point of view. That's why we're looking from above. And this is what is used in the comparison operator for the shadow mapping in order to generate the shadows. Because remember, in the theory, the whole idea is that if the Z value for a pixel from the light's point of view is, for the object that you're rendering is greater than the Z value in the depth map here, then it's lit. It's in shadow. If it's less than the depth value, that means it's closer to the camera, then it's lit. So that's why the top of the pill ends up being lit, because the Z value for its geometry is less than the Z value in the shadow map. So this is how we determine whether there's shadow on the surfaces of objects. Look at the lecture notes to find this out. Remember, the theory holds, even though the implementations are Direct 3D, this one here is actually valid for Unity as well. Same theory. Implementation is different. So moving on, we've got our shadow map. Now we have to deal with actually doing the shadow mapping on the objects. So if we have a look here, we have a shadow map material, which has an associated shadow map shader. This is where all the magic happens, and as you can see up here, the shadow map comes in as a texture. This is the render texture that we see in Unity over here, back in our assets. So going further down in there and back to the code. All right, there's some lighting stuff. That's just to generate diffuse shading on the surface. Nothing special, we've seen that before. There's our shadow map sampler. There's a couple of bits and pieces that we'll use. So first of all, we worry about the size of the texture because we're going to search inside the texture. We need to know what the size of 1 pixel is. The other thing is there's a bias variable, which I get to in a minute. I'll play with that. There's a projection matrix variable. Now this is the projection matrix for the light. I'll get to that in a minute. And then we have to worry about the far and near clip planes. The reason why we do this is because we've got to worry about Z values. And for whatever silly reason, the Z values come through in a non-linear fashion. We have to linearize them again to do the appropriate comparisons here. You need to be aware of this because you're going to have to modify this shader. So be aware of the linearity effect that I show later on, also the linearity code. Standard sort of inputs, positions, normals, and texture coordinates. Note the output from the vertex shader. Standard position and a color. We're coloring the surface. But the big thing to note is the projected texture coordinates. So remember, as according to the theory, the vertices are being projected into the light's space so that we can compare them with the depth value in the light space. So we can see whether that projected value is ahead of anything in the shadow map. Ahead, that meaning the Z value is less than what's in there. So the shadow map vertex shader, straightforward again. Just take the positions, project them, do the usual stuff with the normals. I'm doing a diffuse component, so I've done some lighting here, and blah. Then we get to the need to project our vertices. So note, we're doing another transform on the input position. And what we're doing is, first of all, we're transforming it to its position in the world. So this accounts for any transformations that may have been scripted into the object by you as the programmer. Then we apply to its position in the world the light matrix projection and view transform. So that means that the positions that we see in the main camera's point of view, so what we're seeing here now, these objects, actually has that transform applied so that they can be moved into the shadow map space to be compared with what's there from the light's point of view. And this is the key to shadow mapping. That's the transform you've got to understand. So as well as outputting our values as per normal, we just project into the camera space. There's another projection we do, but the matrix is not the standard transform. It's the light transform. So that means the vertices on these objects here get pushed into this space, and we can start to compare them. We can actually say, is that Z value less than the value in the shadow map? So that's the vertex shader. We get into the pixel shader, and what happens is the projected values come in on the input. It's all good. And we apply a transform, a viewport transform, to bring them into texture space. So we see here that the projected values x, y, first we project them by dividing by w, then we multiply them by half and add half. So what we're trying to do is get them to move from being between -1 and 1, and we're getting them to be between 0 and 1. This means they can be used as texture map lookup coordinates. So that's the purpose of that. Now we do the same, we project our depth value. It doesn't need to be transformed because we're taking it with us. So this means that it's not going to be changed by doing this. So we just simply divide by W and we end up with the depth value. This is the depth value of the vertices from the main camera's point of view. But we are now comparing them in the light space's point of view from being projected. Now that depth we now have to linearize. So you don't have to, look it up. I, again, ripped this from a website by a guy called Hummus. Just look it up. but this linearizes the depth value that comes through the projection process, so that when we compare it, we can compare it easily and right evenly through the light volume with the one in the shadow map. So that's why we got this scene depth variable. Moving right along, we then do some processing to get the appropriate texel position, and then we grab some linear interpolation features from our texture position, and then use that for later linear interpolation of the shadow map samples. We take 4 samples. It's a cheap method, but it works okay, so that we can overcome some aliasing. If we only take 1 sample, we're doing point sampling. You remember from texture mapping, that's a bit dodgy. So what we're doing here is a very simple bilinear interpolation of 4 samples from the depth map, from the shadow map. And what we then do is for each one of these samples, we simply say, okay, that value plus a bias, is it less than the scene depth from the projected values up here? If it is, then the shadow coefficient is equal to 0. If it's not, the shadow coefficient is equal to 1. So what this means is if it's 0, it's going to be in shadow, because we multiply the final color by it. So we linearly interpolate these values and then take that shadow coefficient and multiply the output color by it and spit it out to the screen. And this gives us the scene we see in front of it. So as you can see there, if I move it around, shadows are generated appropriately. And so what it's saying is, okay, from the light's point of view, the top of the teapot, its Z value is less than the depth value in the shadow map. Okay, so that means it's all fine and Jim dandy to render it in the basic color. However, we go directly underneath the teapot. We get the Z value of this point here on the plane and compare it to what is over in the shadow map, and you'll find that it's not less, it's actually greater. Remember, the background is whiter than the teapot. But the pixel value here, the Z value here, is not from the shadow map. We've projected it from the vertex and pixel information here. And so therefore, what happens is the Z value here is not less than what's in the shadow map. Therefore, it's in shadow. The shadow coefficient ends up 0, and that pixel gets drawn dark. That's how shadow mapping occurs. So, going back to the code, what you will have to do for your assignments is you're going to have to insert into here. This is for one light source. So you need to look at this code and modify it to work with a number of light sources in a similar manner to the way you did spotlights for the first assignment. Okay, but you'll also have to accommodate the fact that your sun is a different light source to a spotlight. So these things you just have to accommodate. Alrighty, so that's the shadow map, and now I'm going to go back and let's have a look at just incorporating another object into the scene. So we've got a few objects here. I mean, in the end, as you can see, this teapot is just another object that I've imported. So I'm going to import another teapot. Go down here. It should be in there. Okay, so there's our teapot, and we've imported another teapot, WT teapot 1. So we can just drop and drag it into the scene. And as you can see, what's interesting is that it's already projecting a shadow onto the base there, but it's not getting any shadow itself. The reason is it doesn't have the right material on it. Okay, So just be aware if things stuff up. Check that you have the right shaders on your objects. So, but as you can see, the right shader is on the object for the plane, so it gets the shadow cast properly. And of course, the other objects should accommodate its shadow as well, as we can see here upon the cylinder. So going down. Now, so what we need to do, it's pretty straightforward. The object needs to have the shadow mapping material applied to it. But it still doesn't have proper shadows. That's because the projection matrix isn't set properly and it's not transforming its vertices appropriately. So I'm going to add the shadow mapping script to it. Sometimes this requires a bit of a kick, so I'm probably going to turn it off. And of course, when you turn things off, they disappear from the play mode. So just quickly doing that again, and at dropping shadow map onto it. That's all good. It's got a mesh renderer, excellent. Shadow map and the shadow map here, and the shadow map. There's the depth map here, so that's all good. So fingers crossed. We can see that it's now receiving shadows. Okay, as you can see now, before it was grey and looking red and whatever, but now it's getting shadows actually on its surface, and so it's self-shadowing. Interesting point to note that you'll see that option on some objects inside the inspector, where they talk about actually, as you can see here, mesh renderer, cast shadows, receive shadows. So my guess would be this is for the internal shadowing that is done by Unity. And the reason it needs that to be turned on is that for the internal Unity section, so if I turn this off, it should have no effect. Why? We're not using the Unity rendering pipeline. It's generating its own shadows. And therefore, I would surmise that these things actually turn on the internal constructs for Unity shaders when you drop and drag the standard shadows into the scene. But as you can see, you can turn it off. And I mean, I can turn off shadows for this teapot by just simply getting rid of the script. And then I think we'll find, no, it's left with an instance. If I put that back on again, oh no, it's being painful. So if I make that baby diffuse, yeah. So now the shader's not right. It's not getting any shadows because we need the shader to work for it. And if I drop onto that now, and if I look at the, it's still got the shadow mapping script on it. So if I get rid of that in this one here, should find that it's not receiving any shadows because the shadow mapping script's not turned on. So, alrighty, again looking at my script. So, this means you should have enough information from this video to get the shadow mapping working. Have a look at the lecture notes with the theory. The theory holds here. There's nothing special. Okay, only the code has changed. We don't use Direct3D, we're using Unity. And that should conclude the rest of this video. Thank you.